again, today is our last bit of new information that we're going to have to learn. Okay, so just sort of explain how this is going to go down. Next week we will spend each day next week reviewing one of the past 3 chapters that we just did, and then we will have our third exam on that next Monday, May 6th. All right, and then that Wednesday is your final day of instruction for the spring semester. The following week will be a cumulative final exam. Okay. So we'll do exam 3 on Monday so that I could race to grade them all and get them back to you on Wednesday. What's up?
5-6 is Friday.
Oh, shucks. Okay. What's that Monday? Is that 9?
Yeah.
Yeah. Okay. My bad. Ooh. Good call. Good call. So, yes, the 9th, yeah, that makes sense, because the 11th is our last day of instruction. Yes, good call, thank you. So our exam 3 will be on the 9th. I'll race to get them back to you on Wednesday, and then we'll have our cumulative final the next week. The best way to study for that cumulative final is your past exams that have been graded, as well as, right, for each exam we do that review, and then I post that same sort of assignment onto Canvas, but with slightly different problems, right? So there's that bank of past like quizzes that you can do for each chapter as well. You can see how I pull questions from those review assignments for the exam, all right? Like I said, the course is going to be tricky enough without me having to be tricky about what it is that I'm going to be asking you. So I don't mind making it very clear what I expect you to do. So again, it's just going to be exactly like those past 3 exams. Make sure you know how to do those problems. Good news is like Unit 1 stuff, we've been doing it so much, it should be pretty second nature at this point, right? Drawing bond line structures. I think that we're all pretty much experts at that. Making sure carbon doesn't have, 5 bonds or something like that. That was something we spent a lot of time on in that first unit. So I think that one in particular we've kind of beat to death. This new stuff, as well as the reactions that we learned in Chapter 2, or in Unit 2 rather, are something to focus on. All right, so we got one more set of reactions. Again, we're talking about aldehydes and ketones. These are what are called aldol reactions. All right, and before we can get into the reaction itself, we have to talk about this property of ketones and aldehydes called enols. Okay? A ketone is always in equilibrium with what's called an enol. A ketone or an aldehyde is always in equilibrium with what's called an enol. Let's see if we can pick this name apart real quick. What do we think the ene corresponds to? Looking at my enol here. What are enes? Alkenes. Bueller. What's up? Double bond, right? So alkenes have this double bond. So an enol is a double bond. The ol corresponds to the alcohol group, right? So an enol is a double bond located right next to an alcohol. Okay. This is an intramolecular rearrangement. So the formula for this compound over here would be C3H6O. Same over here, C3H6O. If you remember back to Unit 1 stuff, we would have called these structural isomers of one another. But really it's just this intramolecular rearrangement where one of the hydrogens from this neighboring carbon goes up here onto this oxygen, and you have the movement of this double bond over here. Okay, so every ketone that you have, it's constantly rearranging itself. It's in equilibrium with these enols. This equilibrium very, very, very strongly favors the ketone side. Okay, but it turns out that enol is still kind of important for the chemistry of these particular molecules. All right, so this is a phenomenon that's kind of seen a lot in chemistry where, yeah, totally the dominant species, if you have a solution of acetone, which would be this molecule here, 99.99999% of it is in that ketone form, right? But even if there's only 0.0001% in that enol form, that can still correspond to the reactions of that particular molecule. Okay? So again, before we dive into these reactions here, let's make sure that for a given ketone, we can draw its enol. All right? So I'm going to put down a ketone here. And we're going to draw its corresponding enol. All right, and again, if we want to be trying to be better about being more explicit about our strategy here, we're going to convert, well, I guess so, actually first we're going to draw our carbons. Draw our ketone or aldehyde. All right. Now I'm going to convert my carbonyl bond, carbon-oxygen double bond, into just a carbon-oxygen single bond, right? That carbonyl oxygen needs to become an alcohol. All right, so I'm going to convert my carbonyl oxygen to an OH, and then I'm going to convert that single bond, or double bond rather, to just a single bond. Now I need to draw a new double bond. To what was formerly my carbonyl, not oxygen, sorry, carbon.
We have to draw two.
So in this case, whatever side you picked, this molecule would be symmetric, right? If I picked it over and flipped it like a pancake, it'd be the exact same thing. Okay, so if we have this symmetric ketone, we can do a few more tricky examples. Actually, let's do one more simple example to make sure we have this down. So using our strategy here, draw me my enol. Convert that carbonyl to an alcohol, and now I'm going to make a double bond. That double bond importantly has to be located like right next door, right? What was formerly the carbonyl carbon has to be involved in that double bond. I can't move it, down there, for example. All right, so then maybe one that might be a little bit trickier. All right, so I have these two potential options for where my double bond is going to go, right? Because now this isn't a symmetric molecule. So let's just draw them both and see what we got here. So I'm going to make this into an OH. Draw my double bond there. Make this into an OH. Double bond there. Okay? One of these structures has a major issue. take a second and look at it and see if we can't pinpoint what's wrong with one of these two structures. Exactly, right? So this one here is trash because my green carbon would have 5 bonds associated with it. We gotta remember our basic bonding rules, right? Carbon definitely can't have 5 bonds. So in this case, there's only this one possibility, which would be this one here. Okay, because again, if the double bond tried to form on the other side, we would just have way too many bonds for that particular carbon. Okay. Another possibility would be something like this. Okay, and again, I have these two possibilities depending on which side I want to form my double bond. Okay. Now in this case, there's nothing illegal about either one of those, okay? But one of them is more stable than the other one. Does anybody remember our rules for like stability of alkenes, where our double bonds like to form? The more highly substituted, right? So the more highly substituted an alkene, the more stable. So even both of these can form, but this is indeed going to be the major versus the, oh, no, I lied, holy, hello. This would be the minor, and this would be the major, because again, this is more highly substituted. All right, so those are two tricky situations that we want to sort of make note on. Number one, don't do anything illegal. I mean, a good rule for life, but especially in chemistry, okay? Don't do anything illegal. We can't have more than 5 bonds on our carbon, right? And then 2, even if they, we do have these 2 options, we're going to choose the more highly substituted enol. Okay. Next thing we're going to talk about are enolates. All right, and these are now going to be ions. So let me just sort of show what happens here. It turns out that if you have an aldehyde or ketone, that hydrogen that we saw doing that rearranging, right? When we saw our enol, this hydrogen was migrating. Okay? This hydrogen turns out to be relatively acidic. What do acids do? Donate, accept protons. Which one's an acid? Proton donors, yes, exactly. Bronsted-Lowry definitions, so all the way from general chemistry. Excellent, yes. Acids donate protons. So something that's very bizarre about ketones and aldehydes is that this hydrogen right here, what's called the alpha hydrogen, so this is the carbonyl carbon, the carbon right next door is what's called the alpha carbon. All right, these alpha hydrogens are relatively acidic, which means that they can be removed by a base. Okay, so if I have a base, I can remove that hydrogen and create what's called an enolate. Okay, really this is a carbanion where you have this negative charge on a carbon. That's something that's very bizarre. No, carbon really does not like to give up its hydrogens. Okay, this sort of, under regular circumstances, these carbanions are terribly unstable. They're literally the strongest base that you could possibly have. But there is an exception with these ketones and aldehydes, because this charge right here can be stabilized through resonance, where that negative charge jumps up onto that oxygen. Okay? These two structures are in resonance with one another. All right, and let me just draw. We said that this was an enol. Notice that my enolate is the same thing, just with that hydrogen removed, forming that oxygen, that negative charge on the oxygen. Right, so this is an enol, this is an enolate. All right, but importantly, these two structures, if you kind of remember how resonance works, it's not like one of them's true at one time and another one's true at another time. They're both true at the same time. This has to do with like this fancy quantum mechanics of how electrons work, how they can spread themselves out and be in more than one place. So these enolate, when we refer to the enolate ion, it seems like we'd be talking about this thing here, because that's a deprotonated enol. We're actually referring to both of these because they're in resonance with one another. Okay, so both of these would be considered the enolate ion. These two structures are in resonance with one another. Okay, so I'm going to give you a ketone, and you're going to draw me the two resonance structures of that enolate ion. All right, so it doesn't really matter which one you put first, but again, the whole idea is this hydrogen, this alpha hydrogen is going to be removed, putting a negative charge on that carbon, and this structure is in resonance with this enolate ion. Well, they're both enolates. But now we kind of draw our enol, the skill that we just talked about, but we're going to erase that hydrogen and give it a negative charge. As long as it's the one right next door to the carbonyl group, then no. But it does have to be, right? So this is the carbonyl carbon. One away are what we call the alpha carbons. It has to be on one of those alpha carbons, right? Because if it wasn't, if it was further away, then it wouldn't be resonance stabilized by that carbonyl group, right? That pair of electrons wouldn't be able to do this little jumpy jump here. So it's the stabilization of that negative charge onto that oxygen that allows these to form. Resonance, remember we talked about with our aromatic compounds. Resonance means stabilization, right? If you have resonance structures, that's just this added level of stabilization. So again, carbon usually doesn't like to lose its hydrogen, but with the case of aldehydes and ketones, specifically that alpha carbon will, because that negative charge is resonance stabilized. Cool. So now we can actually talk about our reactions, our aldol reactions. All right, I'm going to warn you, these are one of these ones, not unlike the Grignard reactions, where you're going to look at this product and be like, what the heck? All right, because you're forming new carbon-carbon bonds, which means that we're going to get this big, ugly structure at the end of the day. But just like our Grignards, if we sort of take a step back and just do it step by step, figure out what's connected to what, it's not so bad. All right, so it turns out that if you take a sample of aldehyde or ketones, or for example, acetone, and you drop in some strong base, neighboring acetone molecules will react with one another to form what's called an aldol. And so that, again, I'm going to draw it real quick, and then I'll explain how I got my product. This is an aldol. Okay, and it was two acetone molecules reacting with one another, like two neighbors. So actually, I'm going to draw them both explicitly so we can convince ourselves that we have the correct number of carbons and oxygens. Okay. One of these, because of my base, will form that enolate ion. That would be these three carbons here. And specifically, that carbon with the negative charge is going to form a new bond with the carbonyl carbon on the neighboring molecule. So that'd be this one here. Okay, so again, we'll sort of go through step by step how I got this product, but let's just convince ourselves for a second that we can see that I have 3 carbons in this reactant, 3 carbons in this reactant, so I get 6 on the other side. And I've connected these two from the alpha carbon on my one to the carbonyl carbon on the other. This was formerly my alpha carbon. This was formerly my carbonyl carbon. All right, so let's remind ourselves real quick before we do another one of these what happens if we were to take acetone and react it with a Grignard. We have officially beaten Grignard reactions to death here, so we definitely want to make sure that we're good at them. These are ones that they can tell you right now will definitely be on the exam. Make sure you can predict products of Grignard reactions. All right, so if you go back to our strategy for drawing products for Grignards, you're going to redraw the carbons from your starting ketone, or in this case ketone, maybe aldehyde. What was formerly that carbonyl carbon, that oxygen is now going to be single bonded as an OH group. And you're also going to attach the carbon from your Grignard. Right, so in this case, this would be my product. All right, so we formed a new bond with that carbonyl carbon. All right, I can't just stick a new bond on there. Otherwise, carbon's going to have too many bonds. So when this new bond is formed, it breaks that double bond and it becomes a single bond. That's what's happening in my Grignard reactions. All right, we're going to see the same exact thing with our aldol reactions. So let's take, we'll do just a simple aldehyde here. Okay. So step one, we got to form our enolate. So we're going to make this one right here our enolate, and everybody take a second and convert this aldehyde to the enolate. Okay. Just going back to our previous example, if we were being really good about drawing our enolate, we would always draw these two resonance structures. For these particular reactions, and you do need to be able to do that, okay? So given a ketone or aldehyde, you need to be able to draw me the two resonance structures of those enolate ions. When we're talking about our aldol reactions, though, it's going to be easier to see what's going on if you're looking at this version here, the one with the carbanion ion, the one with the negative charge on the carbon. Because it's this carbon here that's going to form a new bond. Okay? So again, given an aldehyde or ketone, we need to be able to draw both resonance structures of our enolate ions. But when it comes to figuring out the product of our aldol reactions, this form here with the carbon that has the negative charge is going to make it much easier to see what's going on in our reaction. Okay? So if I'm going to make this one an enolate, I'm going to put a negative charge on that alpha carbon. Okay? Form our enolate, and we can redraw it on the product side. All right, so we're just going to redraw that enolate ion. And we're going to connect the carbanion. Y'all know what I mean by carbanion? An anion of carbon. Remember, anions are negatively charged ions. Carbanion to carbonyl carbon of the neighbor. Right? So my new bond is going to be between this carbanion and this carbonyl carbon here. That's my new bond that's being formed in this reaction. Okay? And then lastly, that carbonyl has to become an alcohol. So I'm going to draw this new bond. This was my carbonyl carbon. I guess we should add a step where we draw our, oh, I ran out of room, I get it. Draw in remaining carbons. So in this case, I'm going to make sure to draw this additional carbon, and then my carbonyl group is converted to an alcohol. Okay? And let me tell you a quick way that you can double check that your product is legit. So first of all, we always got that one way that I always tell you. How can we check our product? Count the carbons, right? So that's the first way, especially when you're creating new carbon-carbon bonds. Just count your carbons to make sure you got the correct amount. The other way for these particular reactions that we can check is we're always going to have this 3 carbon spacing of our oxygens. So starting counting here from my carbonyl carbon, 1, 2, 3, I should always have those 3 carbon spacings of those 2 oxygens. If they're any further, or any closer together, you didn't do your structure right. You didn't do your product correctly. Okay? So always count carbons, but we can do this extra check where we're making sure that those two oxygens are 3 carbons apart. All right? So these are big, ugly products. Let's do a few more examples here. All right, so I got to figure out what my enolate is. That means I'm going to put a negative charge on that alpha carbon, right? Really what we're doing this first step is identifying which 2 carbons are going to be connected.
I thought it was the first carbon.
So it's not this one, right? Is that what you mean? That's the carbonyl carbon. It's right next door to the carbonyl carbon. Right? That would be the alpha carbon. Absolutely on the other one, my new bond will be formed with that carbonyl carbon. These are the 2 carbons that are going to be connected. The alpha carbon in one and the carbonyl carbon in the other. Okay? We're going to start by redrawing what was the enolate, because that carbonyl group doesn't change. So again, I'm going to have my new bond there, and it's going to form with the carbonyl carbon on my neighboring molecule. Draw that in. I'm going to put an OH group on that carbonyl carbon. That was formerly my carbonyl oxygen, becomes an alcohol. And then I need to make sure to draw in the remaining 1, 2, 3, 4 carbons. All right, so looking at this, again, I understand that these products that we're creating here are now these big ugly things, right? So it helps to sort of have a ability to check, make sure that we're all good. So number 1, as always, count your carbons. So just double check that you have the correct number of carbons on either side. 2, we can check our connection, right? And it should be between an alpha carbon and a carbonyl carbon. And then lastly, again, specifically for these reactions, we can check our spacing of our oxygens. They should be 1, 2, 3 carbons apart from one another. Cool, all right, let's just do more. These are now a mixture between two different molecules. Right? Only one of these can form an enolate ion. All right, so which one's going to be our enolate? Let's see if anybody can get it. Does anybody see where it is?
It's the acetone.
It's got to be the acetone. Why?
Because if you, like the other one has too many carbon bonds.
Yeah, so this carbon right here, although it's an alpha carbon, there's no hydrogen to remove. There's no hydrogen to remove to form that enolate ion. So the only way that I can form my enolate ion would be with this carbon here. So this is going to be my enolate. So take a second, now given that information, take a second and draw me the products of this reaction here. All right, so if this is my enolate, I'm going to start by redrawing this molecule. And I'm going to note that my new bond is going to be between the alpha carbon of this, and what's the carbon on the other one? The carbonyl. It's cool. We don't get points for pronunciation. Say it whichever way. There are so many chemistry words that I pronounce incorrectly because I read them in a book first and they just got jammed in my head, like infrared spectroscopy. Who knew it was infrared? I don't know, but I still can't say it correctly, I swear, after all these years. Anyways, pick one and roll with it. So then I'm going to make a note that my new connection is here. I got to do one more thing. What's wrong with that carbonyl on this side? That carbonyl carbon.
An alcohol?
Right, so this, in the process of forming that new bond, this gets converted to an OH group. Okay, and we can check, we can count our carbons. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We can make sure that our connection is between our carbonyl carbon and our alpha carbon, which I got them colored so it's easy to see. And then lastly, we can check for this particular reaction that we have this 1, 2, 3 carbon spacing. All right, so let's do another one. Different problem, not the same problem. All right, so I'm going to pick one to be my Enolate, so that means that my negative charge is on this alpha carbon. Now I'm going to connect the alpha carbon on one to the carbonyl carbon on its neighbor. With aldehydes, because there are less carbon bonds already, they tend to be like a little bit neater when you draw your structures. For ketones, they're going to be a little bit more crowded because now I'm going to have 4 bonds on this particular carbon. So I'm going to draw in, so this is my carbonyl carbon. I'm going to draw in my remaining carbons as well as put that OH group. So again, things are a little ugly and crowded, but nonetheless, this is my product. All right. We're going to want to work backwards on these as well. And again, the key to life here is going to be that 3 carbon spacing when we're working backwards, right? If I start counting at this carbonyl carbon in my product, 1, 2, 3. Okay, so start counting at carbonyl in product. Your new bond that you just formed is always between which 2 carbons? If I look up here in my counting, which 2 carbons is my new bond formed between? Where's my new bond? 2 and 3. So if I do this strategy, if I start counting at that carbonyl carbon, my new bond is always going to be between carbons 2 and 3. So let's say that we're trying to work backwards from this molecule here. Try to identify where that new carbon-carbon bond is. That'll help us figure out what our 2 reactants were. All right, start counting at that carbonyl carbon. 1, 2, 3. So that means that this is my new bond. All right, always between carbons 2 and 3 if you start counting at that carbonyl carbon. So if I'm trying to figure out my products, or my reactants rather, I'm going to break that bond. Right, I've identified what bond was formed in this reaction. So if I'm working backwards, I'm just going to break it. This was my alpha carbon of my enolate. And what am I going to have to do to this molecule here to convert it into the reactant that was actually used? Exactly, right? So I form that OH bond in the reaction. If I'm working backwards, this needs to become a carbon-oxygen double bond. All right, so identify that new bond, break it. All right, you can figure out which one was your alpha carbon. And then the one with the OH group, you're going to have to reform that carbonyl. All right, so we kind of rushed through that last bit. We'll pick that up on Monday. So next week's going to be review week. So we'll start by reviewing chapter 9 so we can close out these sort of working backwards things and get really good at these particular reactions. You can start that particular assignment, especially just what would be actually the 3rd problem in it, the forming products. But nonetheless, we'll sort of pick up with this stuff on Monday because we kind of rushed through it.